technically I probably could reassess all the limit standards, but I'm too lazy to test you guys on it, right? So the limit stuff will sit in the relevant stuff, but I trust your guys' ability to get the limits right on the final when I'm testing everything all in one little holistic set. So limits are important, right? Because every test is a limit. So we're going to start with sequences. Sequences, I'm looking for a few things, right? So I'm looking for a 4. I need you to identify the general term from a list of sequences like we had on the quiz. To do that, you're expected to know a few things, and this is how I would do it if I'm struggling. You're expected to have memorized linear terms, right? So if you're adding the same constant each time, you have a linear relationship, so you should be able to identify that linear relationship, right? 2n plus 5, whatever that setup is. Quadratics. You should have your perfect squares memorized, but there are other ways to catch perfect squares. One is if you can factor it, and the factors have a linear relationship. It is something that has a square, right? So if I'm writing something, if I'm trying to build it from scratch, like a weird n squared thing, I might start with like 1 times 4, and then 2 times 5, and then 3 times 6. And that's how I'm going to come up with the denominator that comes from an n squared term. So if you can't see a pattern, but it looks like it's increasing kind of like an n squared, like check the factors and see if there's a linear term, right? Every factorable quadratic will have that feature. So that's an easy way to catch that. You can also recognize it if you see a pattern where you are adding something, but the number that you add increases by the same fixed amount. So if I were to take these numbers, so we have 4, 10, 18, the next one is 28. What I notice about these numbers as a pattern is that I add 6, I add 8, I add 10. When you see that, right, you're adding something, but it's going up by the same amount, right? That next level down is a +2. That's also an n squared type pattern. So it tells you to look at the factors. Okay. Cubes will work similarly. You should know your perfect cubes. I'm much more likely to just use the perfect cubes or the perfect cubes +1. But if I want there to be 3 factors, you might check, are there 3 factors that are linear combinations, right? Typically that would be something easy, like 1, 2, 3, 2, 3, 4, 3, 4, 5. Right, that's how you would spot cubes. And I won't do it with quartics or anything else, right? You need to know how to spot exponential type things. How am I going to spot like a 2 to the n? What does that look like? Looks like the numerator is doubling each time. If you're multiplying by the same fixed amount each time, if it's a multiplication pattern, that's that amount you're multiplying by to the n. Right? Maybe it's adding 1, maybe it's some extra constant, but if you're sort of seeing that amount that you're adding is multiplicative, right? So 2, 4, 8, 16, that's a 2 to the n type pattern. You need to know your factorials and know your n to the n's and have them good to go, up to like 6. The goal of that is so that even if you have a slight adjustment, like I've multiplied it by 2 or I've added 1, you have something where you have the list of numbers there and you can kind of compare it and then see, oh, here's the factorials +1. I have the factorials here and can slot them and see the relationship. That's how you would sort of handle those. So that's the first step, is just knowing those patterns and recognizing it. This test is long, and so my patterns are not as hard as they would be in other circumstances, right? Like if I shortened this to be half the material, right? So you should be able to find the patterns. You have that baseline in. That is enough to get you to a 2. The 2 to a 4 requires you to know how they converge and use sequence convergence tools. So if it's non-alternating, it converges if the limit exists, right? If it goes to a number. It's important because that would be the nth term test's divergence criteria, right? Like if it went to 1. Right? So if I had a sequence of n over n plus 1, that sequence converges to 1, even if the series, if I add up all the terms, that diverges. So I'm just checking to make sure that you understand the difference between sequence stuff and series stuff. So just don't mix them, match them. Easy to say when I'm sitting here, but I would probably look for the sequence problems first and solve them so I didn't mix and match it like without question, because that's the automatic -3. Okay. You also need to know how alternating sequences converge. How do you determine if an alternating sequence converges? The absolute value converges to 0, right? So in that case, That's what you're trying to show me, right? And remember, you're trying to explain it, so make sure that there's enough work there that I understand it, right? You have to convince me that you understand it and that it's not a guess. I don't need a ton of work, but like a little words go a long way. Okay. So if you can do all that, you can do the sequence question. Sequence question will look extremely similar to the quiz. That's part of why I gave you the pop quizzes, so you could see what that question looks like in advance. Okay. So same as the quiz, maybe easier patterns than the quiz, to be honest with you. So, identifiable series. So for 10.2, there's a few things that I look for. One is when you do your p-tests and your telescoping series stuff, right? So the first step is just p-series, right? That's the natural one. Make sure your p-series tests are done correctly each time, right? So the number one penalty I see is sort of like a brain dead thing, right? Like you see it like 1 over the square root of n and you say it converges by a p-test, right? You basically get it backwards because you're not thinking. Right? If you know how the p-test works, you're okay. Right? Sometimes that happens by itself, but more likely that's going to happen in the context of other tests, right? So that's why it sometimes has errors. So you are also expected to be able to recognize geometric series and telescoping series and know how to find that they converge. How does a telescoping series converge? How do you spot it? So see a telescoping series, what you look for is there a way to manipulate it so that you have two functions that are being subtracted that are the same? Right? So it could be 1 over n and 1 over n plus 1. So the function should have the same general functional form. But if I move through the sequence pattern, a positive side and a negative side will catch up to one another. Does that make sense? Like eventually, some of the negative terms would then match the positive terms somewhere in the sequence. So there's got to be a linear relationship there, and it's a specific one, right? So it can't just be that it's 1 over n and then 1 over 2n plus 3, right? Because they will all cancel out with the matching. Okay? So you're looking for a specific format in that case. How am I going to trick you with telescoping series? What have we seen on the homework?
Like if it's
What if I hidden a telescoping series?
you could have like a quadratic. Oh, wait, sorry, no. Like
if it's 1 over a quadratic,
multiple.
you might have to do partial fractions to spot it.
Mm-hmm.
Okay. So that would be an example where you might see a telescoping series. It doesn't have to be a quadratic. Anything that you could have done partial fractions to could be telescoping. Doesn't mean that it is, but it could be. What else have we seen? It's a nice way to hide one. How do I hide subtraction? Logs, right? Logs is the other homework question where you had it hidden inside it. All right, and then geometric series, you need to know the geometric series rule. What's special about a telescoping series and a geometric series? You know the value it converges to. How would I ask for that? I use the word evaluate in the question. That is a clue that you have one of those two series. And before the last lesson, that would have been it. What other series could you evaluate? You have to be able to spot them. So let me write the series you could have evaluated. What is that series? What does it converge to? Is it telescoping? I can't see a way, right? We haven't done anything with factorials. Is it geometric? No. But which of your series do you know about that has an n factorial in it? E to the x. What is e to the x?
X to the n over n factor.
So that's e. What e is it?
E to the negative
E to the negative 3. And it's been simplified. So you can now evaluate every series that is an adjustment of your known series. Like all your known series, a nice trick is that it is also the case that if you plug in a constant for x, you now evaluate it. Okay. So that's another way to prove that the alternating harmonic is the log of 2. Right? Because we know the series for like the log of x or the log of x plus 1. So I can plug in like the value that makes the log of 2 happen and give that series is. Okay. So when you see evaluate, that's the last trick. You haven't seen that. I'd have expected you to make that intuitive jump on an assessment, but you guys are here, so you get a nice little bonus. Okay. So I'm not guaranteeing that'll happen on this test because 10.2 might be something that's cut, but if it's not, that will show up on an assessment for me at some point. Right? Like that trick of like evaluate these 3 series like in each of the types is always tested somewhere. So we have our first little trick. What am I looking for on the nth term test? You check the limit of the sequence, and if that limit is 0, I expect you to recognize that it is inconclusive, that it doesn't tell you that it diverges. That can be tested by itself in the same way that I sort of instructed you to do the nth term test on a specific spot. Or it can show up in another spot. Where else does it show up? If you're doing the alternating series test, if you punt on the nth term test within the alternating series test, you lose credit on that too. So just be thoughtful about that. If you punt. So if you do poorly on the alternating series test, there's an automatic penalty coming on 10.3 too. Okay. Assuming it's that part that's missed, right? Like if you do the nth term test in the alternating series and say, and so it converges, right? And skip the rest of the alternating series test, I'll give you an nth term test, like penalty too.
Oh.
Does that make sense? Like you do both parts, it's fine. But if you skip the second part where you show it's decreasing, you're like, the sequence went to 0, so it converges.
Oh, okay.
You lose credit on both alternating series tests for missing half and nth term test for not knowing the nth term test rules. Okay. So that doesn't happen often, but figure we're going to tell you all the tricks. Okay. Integral tests. What has to be true to do the integral test? Decreasing. I may or may not require you to prove it, right? Because proving decreasing can be quite tedious. But the instructions will be clear, so read the instructions carefully around it, right? So don't prove it if you're not asked. I will ask you to say those words, and you better not be wrong. What function are you going to have in a series that isn't decreasing most often? So some of you done the 100 series. What functions are in there that aren't decreasing? Functions I'm looking for are wiggly.
Like
sine and cosine. Sine and cosine of any arguments, even if they converge, cannot be integrated. They are not decreasing functions. They oscillate, even if they oscillate to 0. That is the primary example of a function that you may not do the integral test on without a large penalty. Right? So if you're told to do something on functions and you get to choose, that would be the one major integral test penalty, is trying to integrate something with sines or cosines. You may not ever. Okay. So I can't think of a version of sine or cosine where you could adjust it and turn it into a purely decreasing function off the top of my head. Okay. So otherwise, how do you know when to do the integral test if I don't tell you?
it looks like an integral.
It looks integrable, right? I don't want that to be too hard, but it's a little hard. So be thoughtful about whether something can be integrated if you have a choice, right? Like it should be something that is doable in a reasonable amount of time, but that doesn't mean that it's going to be the easiest thing in the world to spot. Okay. For comparison tests, what's the trick with a direct comparison test? Sometimes it's inconclusive. You need to be very careful with your greater than or less than math and understand what it implies, and that you're being both correct in what is bigger and what is smaller, and drawing the right conclusion from it, right? Either of those is probably the only way you'd get a direct comparison penalty that's meaningful. When have you seen that you have to do a direct comparison test? So your example on the quiz could only be done with direct comparison. What was true about the quiz example I asked for? Had a log. The way you spot a direct comparison, because I don't generally like it, and lots of things you can do. but the types of functions where you have to use direct comparison is you have a composite function. It's got lots of pieces, and one of those functions is ugly. It's not something that you know how to deal with. Log, sine, right? Things of that nature. And you don't necessarily know what it is, but you know things that are bigger than or less than it that simplify it, right? So our log example on the test is I know that log is bounded between 1 and all polynomials, right? So different direct comparisons would use that relationship, right? Other examples in, say, the 100 series have other bounding situation. What have you seen in 100 series that had bounding?
Like
So-
signs. or-
What specific sign thing did he use direct comparison on?
Like it's less than or equal to 1.
So there are times when certain arguments of sign, you can say sign is bounded between 1 and -1, right? And so if I know something about its absolute value and that's all I care about, right, then I can use that relationship. So that is one of the things that happens with trig, right? So I would think carefully when you're going through the 100, that's something that I would be looking out for, right? That's a trick that I use quite often. Okay. For limit comparison tests should be straightforward most of the time, right? So for your limit comparison test, you have a big mess. The key thing is you care about the numerator and the denominator's powers, right? You just think about in the limit at infinity, what are the parts that matter? But there's one category of functions where it's quite tricky. Where have you seen a tricky application of the limit comparison test?
Oh, the sin x over x.
So the sin x over x limit. The difference for why the limit comparison test works for that function in categories like it is the argument. What was the argument of sine where we did the sine of x over x thing?
1 over x.
It's 1 over x. So there's a big difference between the sine of 1 over n, which goes to 1 over infinity. So it actually goes to the sine of 0, right? It goes to a value, in this case 0, right? So it satisfies your nth term test. And the sine of n. If I just had the sine of n, there's no limit that's going to work in this case, because that goes and oscillates between infinity and negative infinity. So when you see this is the type of thing where you end up with a direct comparison, right? It's not a limiting set. So if you're not sure, both of those examples are in the 100 series, and you should look at what he's doing and think about why, so you can better apply that trick, right? Because that's really where sometimes students struggle with the trick, right? It's like you see these two things, and you're like, why are we doing this here and this here? That's something you need to figure out, right? Because that's a common set of tricks. Okay. So that's our comparison tests. For ratio or root tests, just know what they are and when they apply. Ratio tests, I may only test in the context of power series convergence, right? So otherwise, there is one thing that I look for specifically in ratio tests every time. What is it? So factorials are when you do it, but there is one trick that I use on every assessment for every time I want to use ratio test. What's the trick? What's the hardest thing you've seen with ratio tests so far? It's okay if you don't know, but if you're thinking about how to study, like sometimes I get like, how do you study for these tests that are so hard? Like this is how I study, right? Skill, how is it hard? What does your teacher want to see, right? What I want to see is in the notes. So let's look in the notes, right? Because I think it'll help you guys study for the final. So I go to ratio test notes, and when I review the notes, I don't just review them for like, how do I do this skill, right? I try to extrapolate, like, what's the trick that there's slight versions of that it's like, so let's skim through it and see if we can find it. So we have direct comparison tests, limit comparison tests, and then we have ratio test stuff when we first learned the ratio test. What's the thing that looks kind of tricky? The E thing. You were expected to be able to spot that, and E shows up with what combination? When the factorials are mixed with the n to the n, right? You might have versions of it, right? So you'll see versions of it in the 100 series too, but every time you have n factorials and n to the n's, the limit of E comes out of it with proper work, and I expect to see it. That is a necessary skill for my students. Okay. But that's the kind of thing that sometimes if you're studying, you're like, well, I studied so hard, what did I miss? Like that's the kind of thing that you should be looking for. Like, that was kind of tricky. How could it be a little trickier? And then if you're doing the 100 series, it shows up like 3 different times with different tricks, right? It's like, this time it's e squared, this time it's e to the 4th. Wow. Okay. But other than that, and root test is really easy. Just know that you don't mix and match tests. That's the only error I see with root test, right? Once you do the 1 over n power, doesn't matter what the thing is, you don't get to do the 1 over n power again. It's not whatever power you want. It's literally just 1 over n. And then you complete the test. You satisfy the limit however you need to satisfy it and see does it match. You don't like start the root test and then do another test in the middle because now it looks like a limit comparison, right? So you take the nth root and then take the limit all the way through until you get a number. Okay. So alternating series. The only thing that's really tricky is you need to remember the error of it. What's the error of an alternating series? Next term, right? So just know the fact, right? And then proving decreasing sometimes gets students. Make sure that your sign analysis is without question true. A lot of times students will take the first derivative and then just write less than 0. If that's all the work that you do, you're probably going to get that wrong, and that's a -2. I expect perfect sign analysis. That means that the numerator is unambiguously positive or negative, and the denominator is unambiguously positive or negative. Otherwise, I expect more algebraic simplification, right? So I will give you one that is hard enough to require some work. That is one that tends to be kind of an algebraically intense question, and that's because I'm trying to get you guys to know the difference between proving decreasing and then just taking a derivative and telling me it's negative, right? I have to be able to tell the difference in students who know the two things. So if I just give you like the alternating harmonic, it's not deep enough for me to be able to tell the difference, right? Because in that case, taking the derivative is enough to just say it's negative from there. So expect a good bit of algebra. That question on my set is usually a page of work in full. So when you see the alternating series test, don't just take the derivative and say negative, right? Expect algebra work to be done. Okay. Taylor polynomials, as a standard, has a set of skills that I expect in different combination. Okay? And a number of things could show up, although you can tell we've gotten a whole bunch of notes, right? Not all of this is going to get tested on this test. Some of it's going to show up on the final or on a reassessment quiz, right? We're already in a ton of content. So for Taylor polynomials, I look for a few things. One, you need to know the formula. I'm going to ask for like the 3rd degree Taylor polynomial for some function, right? You better be able to do that and do it quickly. Make sure you've practiced speed on that. That is the kind of thing that you can get pretty bogged down in. I don't expect taking 3 derivatives of the function I give you to take a lot of time. It needs to be like derivative, 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 evaluate at the center. Like that has to happen, and it has to happen in under a minute for y'all, right? Like it's not like it's impossible to do, but like it should flow. You can't sit there and be like, God, what is the 3rd derivative of x to the -5/3, right? Like it's got to cut. So once that's done, you better evaluate the derivative at the center. When I ask for the 3rd degree Taylor polynomial, I expect a cubic function. Then one of the errors that I see that is an automatic -3 is if you plug in the derivative that is a function, right? Like if I ask for a cubic function and you've plugged in the derivative and it's no longer a cubic function, that is a big red flag. It shows a lack of understanding what you're doing. So like if we're doing the Taylor polynomial for square root of x, right? Like my derivative is 1 over 2 root x. That better not show up as is in the formula. You better have evaluated it at the center I gave you so that it's a constant at that point. Does that make sense? So, because then if I plug this in, it's no longer a polynomial. So we've done the same exercise with lines, right? The one thing that made me really irritated is if I asked for a line and you didn't give me a line. So same thing with Taylor polynomial. So that's skill 1. I'm going to ask you to estimate something with the Taylor polynomial. You need to know what to plug in. So don't mix up the x's and the y's, right? You choose the x value that the function gets to. So if I wanted to estimate the square root of 5, I plug in 5, right? For x. I don't plug in the square root of 5. The last skill for Taylor polynomials happens in the context of Taylor series. I expect you to be able to use a Taylor series, if you find it with some other method, to get to higher order derivatives of of the function, right? So you should be able to use the Taylor series for the sine of x squared to get the 42nd derivative of the sine of that function at 0. Right? So we practiced that. That skill is the last thing in Taylor polynomials, is using Taylor series to get every derivative at the center. Right? A common trick is asking for the derivative at a point that is not the center. You better not give me any answer. I'd expect you to recognize that the answer is impossible. So don't just plug and chug mindlessly. Know what the center is and know that you can't get those derivatives practically if it's off of the center. So if I'm using the sine function, what's your known Taylor series for sine centered at? 0. So if I ask for derivatives at 3 pi over 4, you better not provide them using the 0 Taylor series, right? The answer is, I can't find the 42nd derivative of the sine of x squared at 3 pi over 4 because I don't have that Taylor series. Fun trick question. Understand what you can find and what you can't, and know when I have given you an impossible question, and say so. The joy of mathematics. Right. Power series convergence. The only real trick with power series convergence, I tend to use the ratio test each time. Check your bounds and know what that means. Do it every time that you need to. When do you need to check bounds?
Use the ratio
And
another one.
and you get an interval for x. Sometimes you get the interval all reals, right? You solve that ratio test, and instead of there being an x left over, it's, my answer is 0, and 0 is always less than 1, right? So if you have all reals, you don't have to do the bounds anymore. What happens if you do the ratio test and you get like 5? Like you just get a constant that pops out of it that's always bigger than 1. Does it never converge? A power series always converges at one point. When does a power series converge? At the center. So even if the ratio test fails, remember when you're taking the limit and something pops out that the x is gone, right? It goes to infinity or something. That's assuming the x is some constant. If the x thing is identically 0, then you're taking 0 times a bunch of numbers, and that limit is 0, which is still less than 1. Right? So you always converge at the center still, even if the ratio test looks like it fails practically. So.
What was the thing you said earlier about checking for bounds and then if it's 0?
So when you do your ratio test, you check for bounds if you end up with an interval of x, and then you have the edges of the interval. So if I get the absolute value of x is less than 2 once I simplify, then I have to check the bounds in the ratio test, the 2 and the negative 2, right?
Yeah.
But when I don't have an x left over, if the answer is 0, right, we'll have an example like this,
Okay.
then the resulting conclusion is all reals, and there are no bounds anymore. Does that make sense?
Yeah.
So that should happen naturally. I just wanted to cover that again. Mostly for you always converge at something. So as long as you know that, that is not an area I want to be hard unless it's the only place you're doing the ratio test, right? In which point I'll try to have something to tease out the difference between a power series converges and it's not. The only other trick that sometimes happens is if you have a Taylor series, we have not done intervals of convergence for them, but you can, right? There's still power series. You could do the exercise of finding an interval of convergence, right? So that might be worth doing. A fun trick that I have done is not all of your known Taylor series converge for all x. And so I've asked, why is it not appropriate to estimate the log of 4 using your Taylor series? And the answer is that you construct a series that no longer converges. It's not in the interval of convergence. That's normally a final question, but a nice little touch, right? So that's normally not required for 4, but there's a level of understanding there that each of your known Taylor series are not true for all x's. Some of them are and some of them are not. And you guys can figure out which is which for homework. Or do it on the test. It's fine. It's not that hard. So, known power series. I expect you to know what the series are. That's usually easy. And then know how to adjust them, right? So that can include something straightforward, like the sine of x squared, right? Like a composite function. Or something a little trickier, like the sine squared example we had where you have to use some trig identities to chug yourself through, at which point I will accept a number of correct solutions, right? But that would also include the skill of multiplying series that are known, right? So doing them and then finding the first 4 non-zero terms, like multiplying e to the x and sine of x, sits in that standard. So all of that is possible. For a 4, you can't make any errors on the memorization. That includes the starting index, the values. It's all going to be consistent every time, not just when I ask for the memorized series. And it's got to be used correctly. So that first step where you use the series, you have to plug in the value and then simplify it in a step. Right? So if you get the sine of x squared and all you write is x squared parentheses to the 2n plus 1 and never simplify, that's a -1 on the known series, right? You have to simplify the x to do stuff with it. So that simplification step is expected. Okay. For utilizing Taylor series, so 10.12, you'll have to integrate or derive a Taylor series. Don't mix and match, know how to integrate them. Right? And then for Lagrange error, know how to find the Lagrange error bound. You may be asked to choose which error you do. At least one question I'll ask for both, right? Alternating series error and Lagrange error. If I was a good test taker and I got to choose, I would think of which of those answers I was less certain about in the question that had both and use the one that I was less certain about in the question where you got to choose. Does that make sense? Like if you have one question where I just ask for the error, and then another question with multiple parts where I ask for the alternating series error and the Lagrange error, I'd look at that second question first and say, which of those is more likely to be wrong? Which am I less confident in? And then pick the error that I'm less confident in so I get a chance for a 4 while making a mistake. Right? Like if the only time I see Lagrange error is when I direct it and you're wrong, that's a 1. If you chose the Lagrange error correctly in this question and then you made a mistake down there, I can give you a 3 or a 4. Right? So a good test taker won't just jump to alternating series error every time because it's easy, right? Like do the hard thing multiple times. And that's the test. If you know those tricks and you know how to do it, you can get all 4s. Right? I will say this test is the easiest test relative to the possible level that's there. It's because I don't really think series is something that has a bunch of building that you guys need. So it doesn't mean that it is easy because the content is hard, but relative to the level that's expected for say the BC seniors, like what's a reasonable level of content, there's less of a jump for y'all versus optimization, where your optimization questions are impossible, right? Or reasonable. So this is a test that tends to get high scores because of that, because this is closer to what is a reasonable level. So we will go over some formal test questions, but if you can do that, if you need more work for the series convergence, you do the 100 series. For the Taylor series stuff, sometimes you feel a little uncomfortable with that, and that's normal, right? It's kind of weird. The place to go is in the AP FRQs. They're all posted. You search AP Calculus BC FRQs. Every question 6 every year is a Taylor series question. My FRQ version thing for that is basically modeled off of taking one of those and smushing it together with the second years, right? So it's a little longer than a single BC AP question, but all the stuff I ask is in AP questions. So if you did 3, you probably hit all the skills I'm testing, and then you have answer keys associated with it. So that's what I would do for extra practice. But you already have 2 of my test questions, so as long as you can answer them today, you don't need to study anymore. Okay, move those. Okay, so we can start with these.